Okay, so last time we were talking about hidden, right? So we'll discuss more about these things during our practical sessions, right? Because in this topic we are interested in equivalence relations, and this is special because equivalence relation we defined on set of integers, and what relation we defined? A related to B is congruent to B modulo of n. So equivalence relation on Z modulo n is this, right? That is if n divides B minus A. This is what equivalence relation we define on set of integers. And what are equivalence classes? Equivalence classes we denote by Zn and 0 bar, 1 bar up to n minus 1 bar. So right, this is what we discussed so far. So so this equivalence classes, and then we defined some addition multiplication of these classes, and we found that they have additive inverses. Some elements have multiplicative inverse and some elements do not have multiplicative inverse. So which elements do not have multiplicative inverse? So that also we discussed, right? So all of you remember this? We discussed all these things in previous session.
Yes, sir.
Okay, so we'll discuss more about it during our practical sessions, because in practical sessions we'll discuss more problems on this, right? And I will also share with you some PDF in that I have mentioned all these things, and some more exercises I have already shared with you. So now let us come back to our main topic, that equivalence classes, right? And then we want to see something about equivalence classes, some more details about equivalence classes. So that is our next theorem. So let non-empty set, X is a non-empty set, let please keep your mic off. So you should keep your mic off immediately. Anyway, suppose X is a non-empty set, and suppose tilde is an equivalence relation on X. Then we want to see some properties of equivalence classes for X in X is member of its class, right? That is, what is the meaning of this statement? Every element is member of its equivalence class. Right. So whatever is the equivalent class of X, X is a member of that its class. That is obvious, because if you take representative of a class, so representative always a member of that class, right? Second, for if you take any two elements from X, right, then for any xy in X, what I want to say here, Y is member of equivalence class of X if and only if their classes are same. So Y is a member of some class, then equivalence class of Y is same as equivalence class of X, right?
Sir, can you scroll upwards?
Yes, you want statement of theorem. Is it okay? Okay, so is it fine?
Sir. Yes, sir.
Okay, so what is my first statement? If X is any element from set and tilde is equivalence relation on X, then every element is a member of its class, right? If you take any two elements and suppose Y is a member of class of X, then their classes are equal, right? So no matter which representative you select, suppose you have a class and you choose another representative from another member from that class, so they both have same equivalence class, right? That is what the meaning. If Y is a member of equivalence class of X, then their classes are actually same because they are related, right? Third, uh, for xy belongs to X, exactly one of the following is true. Exactly one of the following is true means what? Equivalence class of X is equal to equivalence class of Y, or equivalence class of X intersection equivalence class of Y is empty. So if you do you remember that key equivalence classes are sets, right? Equivalence classes are sets, and therefore for any two elements, either their equivalence class is actually same, equivalence classes are exactly equal, or they are disjoint. There is nothing common at all. If there is something common, then classes are same. So that we'll see. That is, any two classes are either identical or disjoint. Any two equivalence classes are either identical or disjoint. Right. So if you recall all previous examples, then you find that you look at class of some element, then that element is a member of class, right? And also you observe the previous example that there is nothing common in two distinct equivalence classes, right? Do you observe these things?
Yes, sir.
Right. Now, and this is true in general. In general means whatever X and whatever is relation, equivalence relation, this is going to happen every time if your relation is equivalence relation. So let us try to see the proof of these things. So first, what is our claim? What is given? Okay, so given is an equivalence relation on X. So this is our relation. So what is our first claim? For any X belongs to set X, X is a member of its class. This is our first claim. Alright, so this is our first claim. So how to prove this? So let X belongs to X. Choose any X, right? Then X is related to X, Y,
X is a member of set X.
X is member of X, no problem. So, but X is related to
X
itself,
is reflexive. X
right?
will be reflexive.
So, relation tilde is, right? What is the reason? Because the relation is reflexive. Because we are assuming that this relation is equivalence relation, and therefore it is reflexive. And since it is reflexive, every element is related to itself. So, you choose any X in the set X, no matter what X you select, it is related to itself. And hence, by definition of equivalence class, what are the members of equivalence class of X? What are the members of equivalence class of X?
Phi and X.
What are the members of equivalence class of X? Right, so we know that equivalence class of X is the set of those Y in X which are related with X. This is our definition of equivalence class, right? And therefore, if element is related to X, then it is in the class of X. Now X is related to X, therefore X is in the class of X. Correct? Since X is related to X, it is member of class of X, because by definition of equivalence class. Is it clear? Is this clear?
Yes, sir.
Right.
Yes.
So now second point. So what is our claim? What is our claim for xy in set X? Either y is in member of X if and only if their classes are same. So this we want to prove. So first part. First, assume that y is member of X. Right? So y is a member of class of X. Y is in class of X. What is our claim? What is our claim? Their classes are actually same. Right, so their classes are same. This is what we want to verify now. So how to prove this? Suppose y is a member of class. So how to prove that two classes are equal? How to prove that two classes are equal? Basically, classes are sets, right? And when we say that two sets are equal, A and B are sets,
Elements. If the elements in the set are same.
means what? But we cannot say what are the exact elements. We cannot say explicitly what are the elements. We are doing in general sense, right?
They are
So what?
subsets of each other.
Right, very good.
So
A subset of B and B subset of A. Right, so two sets are equal if and only if they are subsets of each other. So this is a general criteria, right? Because we cannot directly see what are the elements in class of X and what are exactly elements. So exact elements we cannot visualize. So we should have some general strategy. So prove that they are subsets of each other. So first of all, we'll prove that, so let Z belongs to class of X. Then we'll prove that key Z is in Y. We are selecting arbitrary element of class of X. Therefore, what is it? Therefore, Z is in equivalence class of X means what? Z is related to X. Is it true?
yes, sir.
Yes,
Right.
sir. Yes, sir.
But what is our
Yes.
hypothesis? So give by assumption, what is assumption here? Our assumption is Y is a member of class of X. This is our assumption. This is assumption. Under this assumption, we want to prove that their classes are equal. So this is assumption. Y is member of X. So by assumption, Y is Y is member of class of, and therefore by definition of class, Y is related to X. Right. So Y is related to X. So, and by since our relation is symmetric, X is related to Y. Am I right?
Yes, sir.
Right.
Yes,
So
sir.
you can write you should write down the reasons, proper reasons to all these steps. So, thus, what is the situation now? Thus, Z is related to X and X is related. Therefore, what? What should I say now? What can I say? What I expect, what I am expecting, I have selected a Z from class of X and I expect that that Z is also member of Y, class of Y, and therefore I can say that class of X is subset of class of Y. And then next
Z
time I
is related to Y.
right. So Z is related to Y
By transitivity.
by transitivity, right? Because our relation is equivalence relation, therefore it is already transitive. And if Z is related to X and X is related to Y, Z is definitely related to Y. But by definition of class, if some element is related to Y, some element is related to Y, that means that element is in class of Y, right?
Yes,
Right.
yes, sir.
So ultimately what we
Sir,
get,
please repeat.
which second last line.
Yes, sir.
So Z is related to Y, right? And what is
Yes,
equivalence? What is equivalence class of Y by definition? It is a set of all those elements in set X which are related to Y. Am I right? Is this definition of class of Y?
yes, sir.
Okay, now what Z satisfies? So those elements which are related to Y, they are in the class of Y. So Z is related to Y, so Z is in the class of Y, right?
Yes, sir.
Right, so very good. So thus, what is the conclusion? Hence, if you choose any Z from class of X, then Z is a member of class of Y. Now what Z I have selected? Did I select a particular specific Z?
No.
No, yes, I just closed my eyes and I just put my hand in the class of X and I found some Z and then I proved that it is also member of class of Y. Therefore, no matter what Z from this set class of X we select, I found that it is member of Y. Therefore, what I can say, the entire class of X is inside class of Y. Right, because whatever Z you select, whatever Z from class of X you select, it goes inside class of Y, and therefore entire class of X sits inside class of Y. That is the first thing. Next, what we want the other way around, right? We want other way around. If you select any element from class of Y, it goes inside class of X. So let T belongs to class of Y. That means T is related to Y. Right, if you choose element from class of Y, it is related to Y. And what is assumption? By assumption,
Belongs to class of X.
so what is our basic assumption in this case? Our basic assumption is, where is our assumption?
Belongs.
So our basic assumption is, uh, assume, this is our basic assumption. Y belongs to class of X.
Class of X.
Right. So basic assumption is Y belongs to, we are talking about particular X and Y, and then for that we are proving something. So therefore Y is related to X. Right. So Y is related to X, and thus therefore T related to Y and Y related to X. This is the situation. And what is the conclusion?
T related to X.
T is related to X, and therefore T is a member of class of X. Right. Hence T belongs to class of Y implies T is in class of X. So no matter what T you select, you just close your eyes and select arbitrary member from class of Y, and then we find that it is a member of class of X. Hence, therefore, entire class of Y sits inside class of X. Right. And therefore, from these two expressions, so hence by 1 and 2, class of X is equal to class of Y. So what we have proved, what we started with, what is our assumption? Y is in class of X, right? And our claim was class of X is same as class of Y. Right, I started with Y is a member of class of X, then I wanted to prove that their classes are equal, and that is what I achieved. So we proved that their classes are equal. Right, so here we wanted to prove if and only if, right? If and only if means this implies this. So one way we proved, now what is the other way around? So secondly, we want to prove that if classes of two elements are equal, then the member is, but this is obvious, right? This we want to prove. Secondly, we want to prove this. This we want, not proved, but it is very easy to see, right? Suppose for X and Y belongs to our set X, their classes are suppose equal, then Y is member of class of X. Okay, let me make more clear. Y is a member of class of Y. Is it true? Why?
Yes, sir.
Because we are already proved in
Yes.
first part. We are already
Yes.
proved in this first part. This is already done. Therefore, we can definitely say that Y is a member of class of Y, but class of Y is same as class of X. That is assumption in this case, right? And therefore, Y is in class of X. So that is what it is obvious to see this. Okay, fine. So what was our theorem? Our theorem was every element is a member of each class. We proved it. If you look at any two elements, if Y is in class of X, it is equivalent to their classes are equal. Right. So second part is done. Now we want to prove third part of the theorem. So what is third part? What is the third part? For what is our claim? For any two elements in set X, right? For any two elements in set X, either their classes are equal or their classes are completely disjoint, but not both. Right. So if you have a equivalence relation and if you look at equivalence classes and you observe the equivalence classes, then you will find that if for Please keep your mic off. Aparna.
Sorry, sir.
So, if you look at any two elements and their classes, right, then the classes are either exactly same, exactly means completely same, or they are separated, but not both at a time, right? Not both at a time. So, you can see in case of Z5, what are the classes? 0 bar, 1 bar, 2 bar, 3 bar, and 4 bar. This you can observe, and you check that 1 bar intersection 2 bar is empty, right? Or you take any two classes here, they are completely disjoint. And you take any two elements, for example, 1 and 6. 1 and 6, their classes are same, right? That means you choose any two integers. In case of this particular relation, you choose any two integers. Either their classes are completely matching or completely same, or they are completely disjoint. That is what happening. That means if this is my set X and I define equivalence relation on this set X, then what happens if I look at equivalence classes, right? What happens? The classes are completely separated. If you recall the example of students in the college, and the relation is two students are related if they belong to same class, and if you construct classes, then what happens? Class of FY, BSc, A division, B division, and so on. There is no common student. Do you understand this? There is no common student among two classes. That is the meaning of two classes are disjoint. There is nothing common. So there is no student who is from FYBSc A division as well as FYBSc B division. So is it clear what is the meaning of this statement? Do you understand this?
Yes, sir.
Yes, sir.
Fine. So forget about this part. So what is our aim? If you have a set and equivalence relation on set X and you choose any two elements, their classes are either exactly same or completely disjoint. So how to prove this? What should be the strategy to prove this? This or this you want to prove. So what should be the strategy? Strategy will be, if not this, then this, right? If one of them fails, then another must be there. So let xy belongs to X. Remember that we are assuming our relation a tilde, which is equivalence relation. Suppose equivalence class of X not same as equivalence class of Y. Suppose their classes are not same. Not same means what? Again, you have to think over it. Suppose I have two sets A and B. When I say that A is not equal to B, sets are not equal means what?
They are not subset of each other.
They are disjoint.
A not equal to B does not imply that A and B are disjoint, right? So sets are not equal does not imply they are disjoint. This is not true, right? For example, if you look at these two sets A and B, are these two sets equal?
No, sir.
Not equal, and they are not disjoint also. Something is in overlapping. Okay, let me give you particular example. 1, 2, 3, 4, because this idea you need to understand clearly, right? When I say two classes are not equal, and look at another set 3, 4, 7, 8. Okay, are these two sets equal A and B?
No. No,
Right?
sir. No, sir.
Not equal. A is not equal to B. And are they disjoint?
No, sir.
No.
No,
Sir.
right? So two sets are not equal
No, sir.
does not mean that they are disjoint. They might be overlapping. There might be some overlapping part, right? So when I say two sets are not equal or unequal, it may happen that they are not disjoint or may be disjoint. That is not an issue. So if I look at another set C, say 7, 8, 9, 10. So A is not equal to C and they are disjoint also. But at the same time, A is not equal to B, but they are not disjoint, right? A intersection C is empty. This is true, and this is not true. So when I say two sets are unequal, does not imply they are disjoint. But when I say two classes are not equal, but they are clearly disjoint, that is happening in this case. So what is our claim? Intersection of these two classes is empty. Do you understand what I want to say? Do you understand what I want to say?
Yes, sir.
Right, because what we want to prove,
So,
so two classes are either equal or disjoint. That means if two classes are not equal, if one of them, exactly one of these condition hold and one of them is true, this or this, one of them hold means what? If this fails, one fails, then second must, or if second fails, then one must hold. So exactly one of them is true, but not both at a time, right? So this is what the our statement, and that is what I want to prove. So if one fails, then second must hold, right? Or if second fails, one must hold. Do you understand the strategy? Logically, is it clear?
Yes.
Yes, sir.
So I am saying that the classes are not equal, then what I must prove? They are disjoint. If either equal or disjoint. If not equal, then must be disjoint. This is what the logically you need to understand. So suppose two classes are not equal, then we want to prove that they are disjoint. This is our claim. This is assumption. This is assumption, and this is want to prove. So this is assumption, and this is we want to prove. So once this is clear, so what to do next? What to do next? Okay, so suppose we want to prove that we are assuming the classes are unequal, not equal. That means they might be overlapping. I don't know, but our claim is that they are not. There is no overlapping at all. They are completely separated. Completely separated means what? The situation is like this. This is set A and this is set B. A is not equal to B, and there is complete separation. No overlapping at all. So we are, in case of equivalence classes, this kind of situation is there. In general, such kind of situation is there. In general, two sets are not equal means there might be overlapping. But in case of equivalence classes, two classes are not equal, then they are completely separated. Right, suppose not. Suppose not. Suppose not means what? Our assumption is two classes are not equal, and our claim is they are disjoint, their intersection is empty. Suppose intersection is not empty, that is x intersection y is non-empty, right? Under the assumption classes are unequal. Under the assumption classes are unequal, and suppose their intersection is not empty, that means they are not disjoint, then there is some, so intersection is non-empty means what? Intersection is non-empty means what?
They are overlapping.
They
They
are
are
overlapping.
invariant
Ah,
and
so
carry
there,
same
there
element.
exists there exists some element. Intersection non-empty means what? So, okay, so now these two sets have non-empty intersection. These two sets have non-empty intersection A and B, but sets are not same. Do you understand? Correct. So two
Yes.
classes two classes have non-empty intersection means there is overlapping. Doesn't mean that the classes are same right now, right? But if two sets, it is like two sets. Two sets have a non-empty intersection. So this is intersection of this is a part of A intersection B. So these two sets have non-empty intersection, but sets are not equal. So we cannot directly say that the classes are equal, right? So immediately, naturally, what happens if when we say that two classes have non-empty intersection or intersection, these two classes are not disjoint. So immediately, naturally, what comes? Ki there is at least one something in common. So there exists T, which is in intersection, right? Then naturally, what comes? Ki the intersection is non-empty means at least some elements are in common in intersection. Right. Suppose there exists T in the intersection because we are assuming intersection is non-empty. Something is there in intersection. So something there is in intersection. That means T is in both of them. Right. T is in both of them. What does it mean? But T is in class of X means what?
T is related to X.
T
T
belongs
is
to
related
X.
to X and
And
T is
T
related
is
to Y.
related to Y. Very good. What is the conclusion?
X is related to
X
Y.
is related to Y.
X
Right.
is related to Y.
Why? By transitivity. Because X is related to T by symmetry and T is related to Y, therefore X is related to Y. And what can I say now? Y is related to X, so Y is a member of class of X by previous discussion, right? So Y is related to X, so Y is a member of class. But if Y is a member of class, by second part, equivalence class of X is same as equivalence class of Y by part 2 of the theorem. Is it correct?
Yes.
Now
Yes, sir.
what is a contradiction? What is a contradiction now?
They are
So we
disjoint.
have to prove they
That
are not equal.
Right. So contradiction to the assumption that equivalence class of X not equal to equivalence class of Y. So we assume that their classes are not same. We assume that classes are not same, and we wanted to prove that the classes are disjoint. Suppose not disjoint, then we came to the contradictory to the assumption. We came to contradiction to the assumption that classes are not same. What we reach, where we reach, the classes are same. Right? So that is what the contradiction is. That means if intersection of two equivalence classes is empty, then we found that classes are equal. If intersection is non-empty, then classes are same. Right? Is it clear? Is there any confusion?
No, sir.
No, sir.
Hence, what is the conclusion? Intersection of two classes must be empty. If it is not empty, then we get contradiction. Thus, what is the final conclusion? In two classes are unequal implies their intersection is empty. Right? So that is what we proved. What is the other way around? What is the other way around? Because we wanted to prove that exactly one of them is true. If not one, then two must be there. If not 2, then 1 must be there. That is we have already proved. Right? If not classes are equal is not hold, then the intersection is empty, that holds. Right? Alternatively, or also if two classes are disjoint implies the classes are two classes are disjoint. Disjoint means what?
There is no
No
common element.
intersection.
Right? Two classes are disjoint, not disjoint, because we in first part what we assume ki two classes are not equal. Then we found that ki they are completely separated, disjoint. What is the second part? Suppose they are not disjoint, then classes are equal. That is what we proved. The same thing we have proved. So the same proof works for both ways. Right. Hence, what is the final conclusion for any, no matter what x and y you select from set X, either their classes are exactly same or the classes are disjoint. Exactly same. Exactly same means completely matching, overlap, completely nothing, nobody, no. So a class of X is same as class of Y means they are completely matching. So, but not both. Both things will not happen simultaneously. The classes are same or they are disjoint. So that is not going to happen. So this is what this statement says. So the meaning of statement is clear. Meaning is clear.
Yes, sir.
To make more clear, if I take set A, B, C, and if I define relation on this set as AA, PB, CC, AB, BA, right? This is it equivalence relation?
Yes, sir.
Yes.
This is equivalence relation. Very good.
Yes, sir.
So now this is an equivalence relation. Right. Now what are equivalence classes? What are equivalence classes? Okay, what is a class of A? First of all, what is a class of A or class of A? A is a member of class of A. By our previous discussion, A is related to A, no doubt. Right? Is is
B.
Yes,
is
sir.
Yes.
is
B.
member of class?
B is related to B.
Is C member of class of A?
No.
No, sir.
No, sir.
No,
No.
sir.
And it is also same as class of B because A and B are in the same class because they are related. Right? From previous discussion, we
Yes.
are sure that class of A is same as class of B.
Yes, sir.
Now, what is class of C?
Only C, sir.
C.
Only
Only C. Only C.
only singleton because C is not related to any other element. So, what is a set of classes?
A and C. Class of A and class of C.
Right? Is X modulo this, right? According to our previous discussion. X modulo this. So, A bar and C bar. This is a set of classes. You can also say that B bar and C bar. Is it true?
Yes. Yes, sir.
Yes,
Because,
sir.
because A bar is same as B bar, no doubt. Now you observe that if you look at two classes, A bar and C bar, what is the intersection? What is the intersection of class of A and class of C?
Five.
M,
Hi.
right.
5.
Now you choose any two elements, whatever elements you choose from X. If I select A and B, then what happens? Their classes are class of A is same as class of B. Right? If we select A and C, what happens? Class of A and class of C disjoint. Right? If you choose
Yes, sir.
B and C, what happens? Class of B and class of C
Disjoint.
disjoint. So what happens? What previous
Disjoint.
theorem says? You choose any two elements, their classes are exactly same or they are completely disjoint. So that is what the meaning is. And therefore, if you look at the set A, B, C, what happens? This set get partitioned into two parts, right? So this set is partitioned into two parts. So this is one part and this is another part. So these two will come together, A and B, and C is separated. Right. Set is get partition. So what I mean to say partition. Before that, uh, I want to make definition. So let,
Sir,
yes,
sir, can you explain that example which you have taken? A overlaps B, and that scroll upside just.
okay. A and B are two sets. A not equal to B does not imply that A intersection B is empty, right? So this is not true. Do you agree with this?
Yes.
Right, because I have two sets like this, they are unequal, right? But still their intersection is non-empty, right? And
Yes, sir.
A intersection B is empty. A intersection B is empty means what? Two sets are completely separated, right? There is nothing common. Now A intersection B is non-empty does not imply कि A is equal to B, right? This is not true. A intersection B is non-empty does not imply A is equal to B. For example, if you look at these two sets, what is intersection is non-empty, but sets are not equal. Let us take particular example A, B, C. This is my set A and this is my set B. C, D, E, F. Now, what is intersection of A and B? A intersection B.
C.
What is a single element? And this is non-empty, right? But A is not equal to B. So intersection is, so these are very elementary ideas about sets, so you can think over it. So you have to
So
be
then
very,
it does not satisfy both the both
which both?
means A intersection B is equal to 5 uh,
And
and one more other
which in they are
which
disjoint.
we have taken. A is equals to B. Sorry.
A is equal to B. So
हाँ.
if in general you are talking about classes or sets, you are asking about classes or sets.
Sets.
Sets. So if two sets are disjoint means there is no overlapping. If sets are separated, so how can you say that sets are equal? Right?
Yes, sir.
So there is nothing overlapping. You look at the set 1, 2, 3, 4, and if you look at set B 5, 7, 8, 9. So these two sets A intersection B is empty, and sets are not equal. They are completely different sets.
Yes, sir.
So what is my point is ki if intersection is non-empty, right? That means if two sets overlap with each other, doesn't mean that sets are equal. But in case of classes, what happens? In case of classes, if intersection is empty, right? The classes are disjoint, then they are equal. That is what the difference. Two classes are not disjoint, that means there is something overlapping. Then exactly classes are exactly same, matching. But that is not happening in general. In general means if two sets are not disjoint, that means they are overlapping, then they are not equal. They may not be equal. But in case of classes, if two classes are not disjoint means if two classes are overlapping, they are completely overlapping. They are equal. Do you understand the difference in general sets and classes? Classes are also sets. That is what the speciality of equivalence relation and equivalence classes. Do you understand?
Yes,
Is
sir.
there is there any confusion? Okay, let me write it again. So two classes are overlapping means not disjoint, then the classes are actually same, completely mapping, completely overlapping. But in general set theory, this is not happening. Now you compare these two things side by side. So now the idea is clear.
Yes, sir.
Yes,
So
sir.
in classes, this implies A intersection B is non-empty does not imply A is equal to B in general sets, in case of general sets. But in case of classes, two classes are not disjoint, then the classes are actually same. Two sets are not disjoint, then sets are equal. That is not true. But two classes are not disjoint, then classes are equal. That is true. Right?
Yes, sir.
Okay. Uh, so let non-empty set so tilde be an equivalence relation on X, right? So X modulo tilde. What is this now?
Set of equivalent
Set
classes.
of equivalence classes, right? So what is this? Basically set of, you choose element from X and look at its class, put the class here, like we did in the case of integers. So 1 bar, 0 bar, and so on. So X is a represented. So let T is equal to uh, T belongs to X such that okay, let the set, let me define it differently. The set of representative distinct classes of X with respect to relation tilde is called as transversal for relation tilde. Transversal. Transversal means what? Ki choose one representative from each class and put that is in the set T. Thus, if T is transversal, for transversal for tilde, then if T1 and T2 belongs to T, then for T1, T2 belongs to T, T1 is not equal to T2 implies class of T1 is not equal to class of T2. Do you understand what I want to say? Key doing now, what I am doing, I am just looking at relation equivalence classes, and I will pick up one representative from each class. So the things will be more clear if you look at this example. X is equal to A, B, C. Right? What is my relation? Tilde is A, B, B, C, C. Let us take the same as we discussed in the previous. So this is equivalence relation. Now what is the class of A? AB, which is same as class of B, right? What is class of C? C only, right? Now what is X modulo this? What are the equivalence classes? Right, there are only two classes, or one can write it also B, C, because same thing as a set they are same. So class of A is same as class of B. Either you write this or this, right? Now I am going to select one member transversal T. Right, I will choose one representative from this class of A. So which representative I can select? I will select A. I will select one representative from this class of C. Right, this is a transversal. I can have another transversal. What is another transversal for this equivalence relation?
B and
B
C.
and C.
B and C. And C has no alternative, right? C will be there in any transversal. But from this class of you can either select A as a representative or B as a representative. So these are transversal. Let me just look at the equivalence classes and choose one representative from each class, distinct class. So we'll get distinct representatives. And therefore, if you choose any two members of this transversal, their classes are distinct, right? If you choose any from transversal, then these elements are not unequal, then their classes are also unequal, right? Because I am choosing. So this is my set X, and due to equivalence relation, classes are formed, and from each class I am going to select one representative, right? And suppose this is some alpha 1, this is alpha 2, alpha 3, alpha 4, right? And alpha 5. So these are representative IM. So what is the transversal for this? Right. Alpha 1,
Alpha 1, Alpha 2, Alpha 3,
alpha 3,
Alpha 4, Alpha 5.
alpha 5. So somebody can select this as a representative, somebody else will select this representative, somebody else will select this representative. So no problem. You choose one of exactly one representative from each class, but not more than one representative. So that is a transversal. Okay, fine. So what is the last point you need to observe? If you have equivalence relation, then we get equivalence classes, and these equivalence classes are disjoint. And therefore, if you look at the set, then these classes partition the set into disjoint sets, right? This is what our final observation, and using this next time we'll continue what to do with this classes, right? So any doubt, any difficulty?
No, sir.
Okay.